Good afternoon, everybody. My name is Giridhar. I am from Azim Premji University. And it's a pleasure to welcome you all this afternoon for Professor Arthur Eisenkraft's lecture. As you know, every year we begin our public lecture series for the year with Arthur's lecture. And this year too, it's a delight that we are sticking to that tradition. Professor Arthur Eisenkraft is one of the most well-known names in the field of science education. And to be precise, distinguished professor of science education, professor of physics, and director of the Center of Science and Maths in Context, COSMIC. Anagrams are nice always. At the University of Massachusetts, Boston. Arthur will need no introduction because let me do a quick thing. How many of you have attended Arthur's lectures earlier? Okay, see Arthur, a fair number of hands, and therefore, and plus the fact that they know you well and the fact that it's there on the note too. All I want to share with you as always is that Arthur brings a great purpose and a great joy to us in the month of January with his lectures. To us it appears he's here on January 11th giving us a talk, but work on this began in September. From the time he prepares that, okay, January 6th to 11th or 5th to 11th, I'm going to be here. I'm going to do 3 days of work in the field. This time he was in Rajasthan. I want to work with the science educators of your team. I want to work with the science teachers in that place. I want to come back to Bangalore. I want to talk to science teachers. I want to visit a school. His program from the 5th of January or 6th of January to the 11th is completely packed. All we say is that give us that one Saturday evening so that you can talk to the Bangalore people of Bangalore at this public lecture service. So from September he starts preparing for that, what he will do, how he will do, and then the lecture. Can I do this? So there's a tremendous amount of preparation and hard work. It appears to us that it's just fun. We laugh through his lectures, we enjoy every minute of it, he's having fun with us, we're having fun. But behind that joy is a lot of hard work. And I think that's something that we can all learn from you, Arthur. It's such a pleasure to invite you, and always.
Thank you so much.
As always, Arthur will speak for about 60 minutes, an hour or so, and 30 minutes for Q&A. And I know Q&As don't have a hard stop, especially today, but Ravi will tell me there's a hard stop.
Well, it's so good to see everyone, and for those of you who have come before, you came back. Thank you. That's so nice to hear. So, when we look at Michelangelo's work, we think to ourselves, Michelangelo created this beautiful sculpture. He invented this sculpture. Out of his mind, he created something. But Michelangelo writes, no, that's not what happened. I didn't invent it. I didn't make it. The sculpture is already complete within the marble block before I start my work. It is already there. I just have to chisel away the superfluous material. And here, this is a beautiful sculpture because you can see him chipping away at the sculpture. But then you take the most famous sculpture, perhaps in the world, the David, and again he said, I saw the angel in the marble and carved until I set him free. He didn't invent this. He said it was there. He discovered it. And what's the difference between invention and discovery? Where do our literature ideas come from? It was the best of times, it was the worst of times. There is enough in the world for everyone's need. There is not enough for everyone's greed in the Upanishads. Was this invented or discovered? Where do our paintings come from? Is somebody inventing them or are they discovering? And I think we say, we invented all this. People invented this. Dance. Where do our dance ideas come from? People invent them, or do they discover them? Where do our sports ideas come from? So I have this slide for Giri here, because he's an avid cricket fan. All I know from cricket is that this person plays somewhere in Bangalore. But that's it. But let's get more to the math and science now. Where do our ideas in math come from? So in math, when you're a small child, first grade, second grade, excuse me, you do subtraction problems. The teacher gives you 12 minus 3, 9 minus 4, 17 minus 9. And then one child says, why does the big number always come first? Can't we do 3 minus 15? So he says, no, no, no. The big number always comes first. And in fact, in the world, the big number always did come first until somebody invented negative numbers and doubled the number of numbers we had instantly. And then you get to third or fourth year, fifth year, and and then we learned square roots, the square root of 9, the square root of 16, and some students said, could we take the square root of minus 25? And I said, no, 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 you can't do that. Only square roots of positive numbers. And then somebody invented imaginary numbers. Said, no, no, square root of minus 25, that's okay, 5i. Even now, we have people here who, if I ask them about dimensions, they'll say, oh yeah, I know what 1, 2, and 3 dimensions are. You have a line, you have a tabletop, you have the 1, 2, or 3 dimensions. And I wonder, well, what about 1.46 dimensions? No, 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 no. Dimensions only come in whole numbers. But in fact, Mandelbrot and other people invented fractals in the 20th century, and this has a dimension of 1.46. We invent different ways of looking at this, and this is mathematics. And now we have the electron, and we all go to school and we learn the electron has a negative charge. The electron is part of the atom. The electron travels around the nucleus. All of these facts about the electron as if it's real and we discovered it, and not that we made it all up and invented it. Our school books are very good at explaining what we know, what's left over after the science is done. They are not so good at explaining how we know. So let's do a little experiment. On your armrests, there are 2 pieces of cellophane tape. And if you lift the top one, if you separate the 2, and you lift the top one and the bottom one, you'll see that there's this remarkable force of attraction between them. And in fact, if you go to your neighbor and you take your top one and your neighbor's top one, then we find out that they repel. That there's an invisible force causing them to attract or causing them to repel. So this is the beginning of our understanding of charge. And we say, how can we explain the attraction? How can we explain the repulsion? So we do the experiment, and we see this, and we have to explain it. So we say, oh, I know. There are 2 kinds of charge. We'll call them top and bottom, because the top piece of tape had one, and the bottom piece of tape had the other. So we'll call them T and B. Well, if you go around the world and talk about T and B, they won't know what you're talking about. So let's use what everybody else says. One is plus, one is minus. And so top it repels top, and bottom repels bottom, and top attracts bottom, or plus and plus attracts, like charges attract. Ben Franklin said, you know, you don't need 2 kinds of charges. We can explain it with 1 type of charge. He said, how? No, we have the top and the bottom. Why 1? He said, no. The top, the tape starts off neutral. The top gets 4 extra things, and the bottom one loses 4 things, and that's how you get the 2 charges. There's only 1 thing moving. And so Franklin makes this jump at our understanding. So we now know there are these charges that do these nice things, and so we start asking questions about these extra things, these charges. How big are they? Where do they reside? Can we isolate them? How do they behave? Are they in all matter? Can we use them for our own purposes? And again, Ben Franklin, who did a lot of studies on this, he said, oh, you know, when you walk on the carpet and then touch the doorknob, you get a shock. That's the same shock as when the lightning hits. It's just a lot bigger, the lightning. But he said it's the same. It's like, really? Those are the same? And again, we begin to understand. If you take these static charges, you can have a machine that makes these charges instead of just ripping off pieces of tape. And when you do that, all of the hairs get the 1 type of charge, and you can see how they separate Just like we had the repulsion of the tape, you now have the repulsion of all the hair. So it looks good and it's fun to do at a science museum. And then we realize that, oh no, the number of charges are conserved. If we start off before touching them with a -10 and a 0, we get -5 and -5. If we get -10 and a charge of +4, then it's -3 and -3. +2 and +6, +4 and +4. It just, you don't lose any, you don't gain any. And just, so it's like this. If you start off with 4 and 0, and you touch them, you get 2 and 2. That's a good trick to know. 4 and just like that for the children. When we try to discover this, charge is conserved. This is an amazing thing. In physics today, we only have found 7 things in the entire world which are conserved. Charge is one of them. If you're able, as a school student, to find another one, you win the Nobel Prize. That's how incredible it is, to find something which always stays the same. Then Coulomb does this experiment way back when, and he says, you know what, I want to measure how strong the force is. When these 2 pieces of tape attract or repel one another, I want to measure it. And so he does a very careful experiment, and he measures it, and he puts an equation down, and now we think we understand about these charges. We understand it so well, in fact, that we can make batteries, which were made in 1790, but certainly we're more familiar with the batteries on the top, and we have cars now which are run by batteries. And then, at a different time in 1820, Ørsted, a teacher, was doing an experiment. And he said, look at the compasses in the top picture. All the compasses point north, as we expect. We use it for navigation. But when he put a current, when he got those charges moving in a wire, he noticed that all the compasses shift. They don't point toward the wire or away from the wire. They point in a circle around the wire. And Ørsted said, electricity and magnetism are somehow related. But of course, the big question is, how does the compass know that the current is there? How is it that how does one charge know that the other one is there? How does this know where to attract? How does it know to go this way? That's a huge question in science, and it's a question that Newton asked with, if I drop my pen, how does the pen know where the earth is? We just say, oh, gravity. Well, that's just a word. How does the earth know where the sun is? And Newton, a great mind, said, I don't answer those questions. That one's too hard for me. But Michael Faraday, who was a poor student, a poor boy, actually he had to leave school at 11 years old. He had a speech impediment and he wasn't liked in school. And he left school at 11 years old. He didn't know much. He hadn't learned much. But thankfully, somebody running a bookbinding store gave him a job. And he got to work in the bookbinding store and learned how to sew books and do all this. And then he started reading some of the books. And some of the books were about science. And so he asked the person who ran the store, there's a little corner of a shop here, a little corner we don't use. Can I do science experiments there? And he said, sure, you can do that. And Faraday starts doing experiments. And he starts trying to explain the experiments. And Faraday, to cut to the chase, becomes arguably the best experimental scientist of the 19th century. He's the best. And he discovers, there's this question of, if you can make magnetism from electricity, if electricity can affect the magnets, can we do something to the magnets to make electricity? That would be nice to make electricity. Faraday's the one who figures out how to do this. But he doesn't know any math. He only went to school to 11 years old. He doesn't know any math. And so there were physicists who said, no, Faraday, you're not really a physicist because you don't know math. He said, but I discovered electricity. No, not good enough for us. You have to know the math like us. what we have to take from the story about Faraday is he was a poor boy who didn't know math. If he came to most of our classes or schools and said, "Can I study physics with you?" we would say, "How much math do you know? You don't know math? No, you can't study physics here. We don't allow you to study physics unless you know more math." If he's working in a store with an education of a fourth grader, and he says to the person who owns the store, "Can I do some science experiments?" they're never saying yes. And so there are children all over India. There are some children who may be Michael Faradays, and we're not giving them the chance to show what they can do because we're saying, "You're not doing it the way we want you to." But because Faraday doesn't know the mathematics, he draws these pictures. He says, when one attracts the other, I think it separates, it sends something out in the space. The space becomes distorted somehow. It's as if there were lines in the space. And they say, lines? Yeah, if I have the lines, I can explain everything I observed. I just like this model of lines. And he draws the lines for magnets, and he draws the lines for positive charges, and he explains how he creates electricity. And then along comes James Clerk Maxwell. Maxwell knows mathematics. And he says, "Let me look at those Faraday lines and put them into a mathematical language." And when he does, when Maxwell takes Faraday's ideas and adds another idea of symmetry, what he realizes is that the electric field will create the magnetic field, which will create the electric field, and then creates the magnetic field, just as Faraday thought it would. But what Maxwell realizes is that when the electric field creates the magnetic field, those lines, it doesn't do it here, it does it here. And when this one creates the magnetic field, it does it here, and here, and here, and here, and here, and here, and it marches across the room. And Maxwell said, "I can find the speed that these field lines move." And when he does that, it turns out to be the speed of light. And so Maxwell says, "I think light is part of this electromagnetic wave and these field lines that Faraday did." And now, not only are the field lines believed to be real, that Faraday invented, but we think everything is fields. We think the fields are more real than the mass. So we have those fields. And then along comes, in the 1897, some of you remember there used to be televisions that weren't this thick, but they were much thicker. And if you turned them off, there would sometimes be a white dot in the middle. Those had tubes in them which could shoot things to the front of the tubes. And it was very nice because we could shoot this thing to the front. We could also have it by using magnets, or we could have it go from the top all the way across, then the next line all the way across, the next line all the way across, the next line, and then we'd say, "Oh no, instead of just lighting up everything, let's turn them on, off, on, off, off, and we'd make a whole picture. The picture could change, and we had television." Well, that tube, it existed, but nobody knew what was hitting the front. And then J.J. Thompson realized that, in fact, it was something he would call the electron. So this is actually J.J. Thompson's voice telling you about what he discovered.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
Thompson discovered or invented the electron. What's good also to remember about Thompson is in the laboratory where he made this discovery, he wasn't allowed to touch the equipment because he was so awkward. Other words, tell us what you want us to do, we'll do it for you. So once we have the electron, we then can explain things like the photoelectric effect, where light can free electrons from substances, or that light can behave like a particle when it does that. In this case, light can hit. That's interesting. Okay, I don't know why that's happening. Anyway, so light can have a collision with this. There it is. Light can have a collision, so the light comes down, it hits the electron moves one way, the light moves another way. And then the question was, well, how big are these charges on these electrons that Thompson discovered or invented? And Millikan does this oil drop experiment, and what he finds is that if he takes an oil drop from a little tiny oil drop, and he can make it go up and make it go down, he can make measurements. Now, it doesn't look very hard. He's doing this through a microscope. And he's trying to keep the same oil drop going for 3 hours, 7 hours, 3 days. And he just did this. I remember my students saying, did he get paid a lot of money for that? I don't know how much money he got paid for doing this, but there was some reason he wanted to do this. And he discovered that these charges, you can have 5 or 11 or 20 or 30, but you can't have 3.5. You can't have 2 1/3. That somehow the charges are one at a time. Similarly, at the same time, we have Ernest Rutherford discovering the nucleus. Now, how did he discover the nucleus? Like this. So, some of you have this piece of paper in front of you. What I'd like you to do is take the piece of paper and have somebody next to you, without looking, see the person on the right not looking, and just take your pen and hit the piece of paper, have the person move the piece of paper, do this 10 times and see how many go in the circles and how many don't. So just do this, don't look, and the person will keep moving the paper, and see how many go in the circles and how many don't go in the circles. I've not usually done this in this kind of laboratory environment, but so I need you to count how many went in the circles and how many did not go in the circles. Out of 10, how many hit a circle? So with a show of hands, out of 10, how many people had 1 hit a circle? 2 hit a circle. 3 hit a circle. 4 hit a circle. 5 hit a circle. 6 hit a circle. 7? 8? Nobody wants to go to the casino? 9? 10? Okay. So, if I add it all up, I'd say about 5 was the biggest, 4 or 5. If you hit the circle 5 times out of 10, that must mean that half the area is circles. I know the total area of your card, it's written on the bottom, is 50 square centimeters. So that would mean the coins would be half of that, 25 square centimeters. And there's 1, 2, 3, 4, 5, 6, 7, 8. So that would mean there's each circle is 3.1 square centimeters. And so if I take that, I know the size of the coin, and therefore I know the size of the circle. I can measure and I can use an equation to get the radius of the circle. So without knowing any one circle, by just dropping the pen, we were able to calculate, and you can measure this, you can take this home, measure it, it's about 1 centimeter, it works. So let me show you what happens. If you could take a moment, and you're on the back of this, draw a square, a little square, very quickly, just, don't take out your scales and protractors, just 1, 2, 3, 4. And let's say not 8 coins, not 8 circles in there. Let's say there's one shape in there, just a single shape. And half of the drops hit the shape. What might the shape look like? Just draw in there what you think the shape might look like. And I'll show you what I mean. Some people will say, it looks like that, because half of them would hit the red, half would hit the white. And somebody else says, no, I think it would look like this. That's also a good answer. Half would hit. We don't know what the answer is, but if half hit, we know that's an answer. Or somebody may say, ooh, that's clever. Half hit, half don't hit. So we'll do that again, but this time, we'll do this now, but what would it look like if you drew a square, and I told you only 10 out of every 100 hit? I did it 100 times and only 10 hit. What might the shape look like? And I think you would agree it looks something like this, or it looks something like this, about 1/10 of the area. So we do it again. And we say, what would it look like if it was 1 out of 100 it hit? And I say, oh, it would be small. It would be something like this. And then at the end I say, okay, let's do it one more time. 1 out of 10,000 hit. And you say, oh, if I draw a dot, that's too big. 1 out of 10,000 hits. Rutherford did an experiment very similar to this. He didn't drop his pen, he dropped these things called alpha particles. And when he dropped them onto a very thin piece of gold, he used gold because you can hammer it so it gets very thin. He didn't use gold because he has a lot of money, so I'll use gold. He didn't have a big research budget, we better use gold. No, he used a very thin, and he dropped these alpha particles. And what he found was that they all went through. They all missed. How many missed? 1 out of every 100,000 hit. 1 out of every 100,000 hit, and all the others went right through. And so 99.999% go through. So Rutherford said, matter is mostly empty space. It appears solid, but it's mostly empty space. And he says, the little tiny parts of mass where 1 out of 100,000 times you hit it, I'll call that the nucleus, the center of the atom. Now, just for those of you who worry about the correct physics and say, he didn't drop out. No. The conclusions are right. He didn't drop the alpha particles, he shot them horizontally. And it wasn't just hit or miss. Sometimes they traveled in paths, hyperbolic paths, and from that he could determine the nuclei. But the conclusions are right. So Rutherford discovers the nucleus. Let's hear from Rutherford. This is a tape of Ernest Rutherford.
The bother is that a nucleus, as you know, is a very small thing, and we know very little about it. I had the opinion for a long time, that's a personal conviction, that if we knew more about the nucleus, we'd find it was a much simpler thing than we supposed. That these fundamental things, I think, have got to be fairly simple. But it's the non-fundamental things that are very complex, usually. I am always a believer in simplicity, being a simple person myself.
So Rutherford says there's a nucleus. Thompson tells you there are electrons. And Niels Bohr says, I think I know how the atom looks now. The nucleus is the center, and the electrons circle around it. And with this picture of the energy levels of Bohr is able to explain the 4 lines that we see from hydrogen. Hydrogen gives off colors, and he gets the colors completely correct. And that's quite an accomplishment. But he does more than that. He also predicts that if the electrons jump from one orbit to another orbit, you could also see very high energy lines. But we can't see those. Our eyes don't detect those. That's okay. Somebody built an ultraviolet detector so you could see them, and Bohr got all the numbers. He predicted the exact numbers. Then he said there's another set of colors, but our eyes can't see them because they're in the infrared. But somebody invents an infrared detector, and once again, Bohr predicted what the colors would be, and everybody said, he's on to something. But of course, new questions arise. What do you mean the electron's in a circle? How does the electron get from one circle to another circle and never be in between? And so it puzzles us. Why are they in the circles Bohr says? He made up some rule, MVR equals NH bar, but why? And then along comes de Broglie. De Broglie's a student working on his PhD, and he has this idea. He says, you know how light used to be a wave? Now light's a particle. Sometimes it's a wave, sometimes it's a particle. Well, the electron we know is a particle. Maybe it's also a wave. And I said, what do you mean a wave? He said, like a wave. And so this is for his PhD thesis, and the question is, do you give him his PhD? And everybody's looking at this saying, I don't understand this. Do we give him his PhD? They finally go to Einstein, who says, he knows enough physics, give him his PhD. But de Broglie says if these are electrons or waves, then on a string they would look like the top pictures, but they would be, to fit like as waves, they would have to be in certain circular orbits and not others. And that's why they're in certain orbits. So he has these things, and then that seems to make sense until Schrödinger comes along and says, I have a better idea. Instead of worrying about the wavelength of the electron, I've invented something in mathematics called the wave function, and I give it this Greek letter psi. And that's the electron. They say, what is the wave function? He said, no, it's just math. He said, no, but you're telling me the electron's math? Yeah, the electron is just math. It's just this psi. It's just this wave function. I say, and can we see the wave function? No, you can't see the wave function. Does it have properties? No, it has no properties. Oh, it has to fit an equation. They say, well, how do we know if it makes sense? If you take the wave function, you can find out how it fits into a box. If you square the wave function, it tells you the probability of finding the electron in certain locations. So if you look at the bottom right diagram, it says that the electron in a box, the electron will go back and forth, back and forth, back and forth. And the probability that it will be in the middle is very high. So sure, that makes sense to me. An electron goes back and forth. If you keep taking pictures of it, if you somehow could, keep taking pictures of it, most of the time you'll find in the middle, a little less here, and at the walls it'd be very rare. So that makes sense. But then Schrödinger says if the electron has more energy, then it's the middle picture on the right. And now the electron's going back and forth, and half the time it's on the left side, and half the time it's on the right side. But you'll notice in the middle, it's never there. The electron will never be in the middle. And we say, wait, the electron gets from the left side to the right side, but is never in the middle. Yes, that's right. But this is not how I imagine It's like, no, this is what we think electrons do. And then we put in the textbooks all these pretty pictures, and we say, that's the probability of the electron in the hydrogen atom. We say, oh, okay, now I understand it. But we don't understand it. So then we do this model. Thomas Young had done this experiment where he sent light through two slits, and he saw that the light would hit in certain locations, the white locations, and wouldn't hit in the black locations. And he said, see, so light plus light can make dark, and that's how we know light is a wave. Davidson and Germer in New Jersey are doing an experiment, and they're shining electrons at a metal. And they're looking to see what happens when the electrons go through the metal. And they look and they say, oh, look at this, it goes here and there. And they're doing their experiments. And then they come to Davison is taking vacation in England. And he goes to England, and he's sitting in the back of this talk, a physics talk. And the person says, oh, and we have this new theory by de Broglie that electrons are waves. And we have the first evidence of electrons are waves from this group Davidson and Germer in New Jersey. And Davidson says, me? Really? I didn't know. I didn't know what these results meant. And Davidson and Germer said, wait, we have better results. And all of a sudden, we start doing the experiment. We send electrons through slits. And as you saw, they keep landing in places, but they never land in other places. The electron lands in some places and not in others. So millions of electrons go through, and they land in some places, not in others. To better understand that, I want to do a quick experiment here. So this, I didn't put coins. I hope people might have, I know this is, you all have 500 rupee notes, but if you have a coin, so we take the coin and we just draw this and that, 1, 1, 1, 1, 1, 1, 1. I'll explain it. So you start at the top one. I flip the coin. If it turns out it's heads, I go to the left one. If it turns out it's tails, I go to the right. Then I flip it again. And I go to the left, or I go to the right of the left one, or I go to the left or the right of the right one. And I do that over and over again. And then I look to see, where do they land? And if we had the time and everybody had enough money to do the experiment, then, or I had enough money to put them at each chair, then what would happen is, if I asked you, where did yours land? I said, who's landed at A? A few people would raise their hand. The lucky people, the people who got heads, 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 heads. The people who got tails, 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 tails would say it landed at E. But most people would say it landed at C. There's a probability most of them will land at C. And that's somehow what the electron does. The electron goes through a slit, and sometimes it goes left, sometimes it goes right, and we have no idea which way it will go. But we know, if we do it with enough of them, how many will land at each position. And we can try to better understand where they're going and how they're going, and there are ways to do that. To make the slits smaller, we can try to understand where they are, but then if you do that, the direction they go is not known, so it becomes more complicated. This is the first conundrum. What causes the electron to travel as it does? If you take two identical electrons and two identical sets of conditions, you get different outcomes. Why won't those electrons behave properly? Why does it, the electrons certainly don't have rupee coins that they're flipping. So what determines where they will go? The second conundrum is if the electron has two slits to go through, it lands in certain places, not in others. And this is the conundrum which people still struggle with today. So when electrons go through two slits, they land in a place. Let me explain to you in a simple way. We take one electron at a time, one electron, and we shine it. There are two slits, A and B, but we're going to close slit B. So if the electron gets to the screen in red, it must go through slit A. And when we do that, it doesn't go straight, there's a probability, but it lands somewhere in the green, always lands in the green. Then we do it again. This time, we'll close off slit A so we know it goes through slit B. And when we do that, now it lands in the yellow, and that makes sense. They all land there. And one was in front of the A, one was in front of the B, that's good. But if we open both slits, then they land in the middle. So let me explain it a different way. If they go through slit A, they land in the green. If we know they go through slit B, they land in the red, in the orange. If we don't know which slit they go through, if we give them an option of going through two slits, then they land in the blue. One more time. If slit A only is open, and the electron only sees slit A, it goes to the top. If only slit B is open, it goes to the bottom. If slit A and slit B are open, it never goes to the top or bottom. It always goes to the middle. And so you have to wonder, how does the electron know two slits are open? So if you only have one slit open, it behaves one way. As soon as you open another slit and say, you have a choice, the electron will never land where it used to land. It will only land in these new places. Now, what we don't know, it behaves one way. When we do know, when we know, it behaves one way. When we don't know, it behaves another way. Our role is determining how the electron behaves. It's not true for a falling ball. You don't have to look to see the ball. It's going to fall. The water will boil. Now, there are people who said, I'm going to trick those electrons. And people are still trying to trick those electrons. Here's the way they try to trick it. I'm going to let the electron see two slits, A and B. They're both going to be there. The electron can go through slit A or slit B. If it goes through slit A, I'm going to detect it, so I'll know it went through slit A. If I don't detect it, it must have gone through slit B. When you do this experiment, they all land where the orange is. If you take the detector away from A, after the slits, take the detector away from A, now they all land in the blue. And this is a very simple trick. Physicists for the last 50 years have been working on more and more sophisticated tricks to try to understand what the electron is doing. Niels Bohr said, if this makes sense to you, then you don't understand it at all. Or another way he said it, those who are not shocked when they first come across quantum theory cannot possibly have understood it. So if you say, that's fine with me, Bohr is saying you don't understand it. So then Paul Dirac comes along and he says, oh, I have a model for the electron. If you do this, then there'll be another, something like the electron, but have a positive charge. And Anderson finds that and does that. Let me give you another example of these wonderful electrons we discovered or invented. Electron tunneling. So normally, if you think of this as a wall and the red as a cricket ball, if I throw the cricket ball to the wall, it's going to bounce back. It's not high enough to go over the wall. It's just going to bounce back. And that's what we would expect from an electron. We hit it against the wall, it doesn't have enough energy, can't get over, it'll bounce back. That's not what happens. Most of the time it bounces back. But every once in a while, it doesn't bounce back, it somehow ends on the other side of the wall. It's like, wait, how did it get through the wall? We don't know. Did it go over the wall? No, it didn't go over the wall. We know it didn't go over the wall. It doesn't have enough energy to go over the wall. But it somehow appears on the other side of the wall. And we know, not just that it appears on the other side, we know how many are going to appear on the other side of the wall. Very, very accurately. How accurately? So that your phone will work. That's how accurately. All of your phones work on this principle that some will get through the wall, and we know exactly how many. So this is just too complex, and it makes us dizzy. So let's just see, can we use this idea? And the answer is yes. We have electric currents and chemical effects. We have televisions and semiconductors. We have superconductors. We have MRI machines. We have scanning tunneling electron microscopes. We use this stuff all the time, and we don't understand it. And then, of course, in 1936, somebody discovered a new kind of electron, and I remember, I think it was Pauli said, Fermi said, wait, a new muon, who, like at a restaurant, it's like, who ordered that? We don't want that. Nobody wants it. We don't like this. We don't need another. We're confused enough. Don't give us another particle. And now we have tauons and leptons and all sorts of things. But we're so accustomed to the electron. We're so accustomed to the electron that the model we have, we feel so good about that we think we understand it. So let's start with the most fundamental part, the part we started with the attraction and repulsion of the tape. And we say, oh yeah, some charges are plus, some are negative. The electron has a negative charge and the proton has a positive charge. And we write that down on our examinations as if we understand it. And so I ask you, and what is this charge? What does it look like? Does the proton have a little plus sign on it? Does the electron have a little minus sign on it? What does charge mean? Is it really a physical property, or is it something we invented to explain these results? And why are there two charges, plus and minus? Why don't we have a universe with 3 charges or 4 charges? Why only 2 distinct kinds? Why can't we have an ABC charge? So in school, we want to ask the questions. In school, we want to ask these 4 essential questions. Well, let me go back. How do we describe it? With a wave function, a mathematical function. That's the electron as we know it. How does it behave? Well, not like anything I know. So the question is, did we invent the electron or did we discover it? So in school, I insist that we assign our students 4 essential questions. What does it mean? How do we know? Why do we believe? And why should I care? The what does it mean we do a very good job with. The electron has a negative charge. The electron's part of the atom. We're very good at this. What does it mean? We're not as good at the how do we know, but that's the important part. That's the science. Let's do experiments and let's try to interpret those experiments so that they make sense to us. And then we get to the why do we believe in the electron. We never see an electron. Nobody's ever seen an electron. We can describe it as a wave function, but the wave function is never observed. The electron behaves strangely, as the double slit experiment shows, and the tunneling. So I wonder, is the electron real? Is truth real? Is time real? Is coincidence real? We pretend all we know about the electron. I don't know what we do about truth, time, and coincidence. Did we invent the electron or discover it? Why do we believe in the electron? It helps us explain experimental observations. It connects charge to light. It predicts the spectra of gases. It has simplicity to it. It is far-ranging. It is part of a larger theory of matter. But the nature of science, it's so unlike anything we've ever seen. Will our model change? Yes, it will. How? I don't know. But here are explanations for the double and slit experiment. What you have is 12 different explanations, from the Copenhagen interpretation to the Broglie-Bohm to the information-based to the many worlds theory. And the bar graph shows you how many physicists believe in each of these. And that's the current state of our knowledge of the electron. So there are a few which nobody believes in. Good. But look at this. Nobody agrees on what is the electron and how does it make sense. So why should we care? Well, we have technologies. We need new technologies and engineers. It's a new way of looking at the world. It's new examples of where our intuition fails us. Was it invented or discovered, the electron? I don't know. Was Michelangelo's statue invented or discovered? Is love invented or discovered? Is the right path, in honor of Gandhiji's 150th anniversary, always choose the right path and speak the truth? Are those inventions or discoveries? The unexamined life is not worth living, Socrates. The electron. David Attenborough said, "It seems to me that the natural world is the greatest source of excitement, the greatest source of visual beauty, the greatest source of intellectual interest. It is the greatest source of so much in life that makes life worth living." And T.S. Eliot, not talking about the electron, but talking about other things, said, "We shall not cease from exploration, and the end of our exploring will be to arrive where we started and know the place for the first time." Thank you. So, do you have questions? Do you want me to tell you what the electron really is? Oh, there's a microphone. Yeah, I can do that.
Yeah, curious to know how these experiments are actually done. like you talked about electrons and, giving them a choice between two slits. Sounds very interesting, but it's difficult to imagine how these are actually conducted. Like, how are electrons separated? How is it all done?
Well, because they're so small, we hire very little children who can pick them up. They're all experiments, and I simplified some of them for this audience. The people here who are physicists could see where I simplified them. But it's very easy to go on the internet and say, I want to know more about any of these experiments and how they're done. But I assure you, they're very difficult to do, and people are still doing them today and trying to interpret them. In fact, one person just wrote a paper, which I liked very much, which explained how the electron gets from one place to another without being in between. Because we say, no, it should be in between. And the analogy she came up with was, when I was in Jaipur on Tuesday, I took money and I deposited into the bank. I gave them money and I put in the bank. When I got to Bangalore, I said, can I have my money? They said, of course. I don't think my money went through Hyderabad. So how did it get from Jaipur to Bangalore? I don't even know what happened to the money once I gave them the bills, because once the bills were there was no more bills. There's no more physical money. There's something else. And it goes to all these places all over the world. I can take the money out when I get home to America. But it's never in between. It's something else. And I thought it was an interesting analogy for me. It was an interesting way of thinking about it, that I said, oh, now I'm more confused about my money. I better watch out. So the experiments are quite sophisticated, but they all can be done, and many of them can be done by many, many people. In the old days of physics, before 1970, everybody could do the experiments. Everybody could do every experiment, and so you would do it, and say, oh yeah, we all got the same result. Now we have experiments that only a few people can do in the world because the equipment to build the Hadron Collider costs so much money, there's only one place to do it. LIGO, the same thing. But these experiments can be done by everyone. And so if you doubt them, go to a physics department at a university and say, can I see how you do this? And they'll show you an apparatus. Yes. Oh, you should take the microphone, I think, here. They're coming with it. Oh, you have a choice. Which one, the left microphone or the right microphone?
But I'm in the middle. So I got it. So could you, from what you mentioned about the accelerator and so on, what exactly are we trying to, do there and prove what is not known, and where will it go? In simple words.
Yeah, so there are two very different parts of science. The relation of science to engineering and the relation of science to just pure knowledge. And we're living in a time now where, well, I guess it always existed, where people say, oh no, we should only do research on things that will provide better technologies for us. We need a better smartphone. Let's invest in that. And it's like, no, I just want to find out about these electrons. It's like, why would you want to find that out? Or I just want, I'm interested in this idea of, is something going on Mars or another planet? And people say, we shouldn't waste our good money on that. Nobody cares. The history of science has shown that that's a bad path to take. The idea of what is the utilitarian value? What is the value of the technology? So I'll give you an example. If in 1860 or 1870, the government said, we need a better form of communication, and everybody could have gone out and tried to discover better forms of communication. Faraday and Maxwell were just saying, oh, look at this, if I move this, this happens. Oh, Maxwell, if I do this math, look what happens. But because of Maxwell, we have radio. Because of Maxwell, we have the microwave. Because of Maxwell, we have X-rays and gamma rays. So it's like, but if you didn't fund Maxwell, who was just kind of interested in this, you wouldn't have the technologies. So the idea of like, no, we will only fund things where I can see what will happen, we will become stagnant. In the 20th century, we had people working on this. They said, you know, these electrons, if I apply a magnetic field, I wonder if I can get them to flip. It's like, why would you want them to flip? It's like, I like watching them flip. But because of that interest in what would happen, we have MRI machines, which we value in medicine. So we study it because, like Edmund Hillary, it's there. We study it because we're curious. It's Millikan with the oil drop. Is he getting paid a lot of money? No, but there's something bothering him. He wants to know. And that curiosity ends up, historically, being extremely valuable for us in terms of technology. But this path of only show me the value of your work now, I think will lead us to have dead ends. Yes?
Can I ask a question?
When you have these experiments, certain experiments, how do you know it's going to behave how do you know whether it's going to behave as a wave in one way and the particle in the other way? What if it behaves the same way it did in the previous experiment?
So are you asking, how do we do the experiments, or the result of the experiments?
So let's say you take the double slit experiment again, and you send the electrons. How do you know it's coming as a particle and not as a wave?
Oh, that's what we don't know. We know we can shoot the electron. We know where it lands. All the rest is a mystery. We don't know what happened in between. We try to find out, but we don't know. And people say, as I said, there are tricks. So they say, I have an idea. It goes through one, if there are two slits open, it goes through one slit, then it goes back through the first one, then it touches the second one, then comes, and that explains it. And everybody who tries to do that, somebody says, no, it won't explain this experiment. So that's why it's still a puzzle. We need, what grade, what year are you in?
I'm in 7th grade.
7th grade. So by the time you go to university and then study more science, maybe you will come up with a solution. But right now we're waiting for someone like you to do it.
A quick question here from the back. In all the experiments being done with respect to the electron, are there studies saying it is the same electron which went through the slit which came on the other end of it? Meaning,
no. So that's interesting. We think all electrons are the same. And so you can't put a little marker, you can't put a little necklace, you can't put a little badge on the electron to see if it's the same electron. There's no way to do that because we don't even know what the electron is, so we can't get it to stand still long enough for us to mark it with a little X. So we don't know it's the same electrons. And in fact, some of the theories, which will really bother you, Feynman had a theory that, we have these electrons and we have these positrons. Maybe the positrons are just electrons which go backwards in time. And maybe there's only one electron in the whole universe, one electron in this whole room, and it just keeps going forward and backwards in time, so we have all the people sitting here. These are real theories in trying so hard to understand something which we don't understand. And maybe the point is the scientific temper that we search for is this idea that, no, our common sense doesn't work. We need something better. And to come up with ridiculous ideas, maybe the scientific temper is, okay, before I tell you that's a stupid idea, leave me alone with your ideas, let's see where it can go. And maybe, well, there was a physicist who, when they had one of these theories in the 1930s, he said, well, it's a crazy idea. Is it crazy enough? We become so comfortable with the science we have that we believe that we understand it and that it all makes sense, and it always made sense. One of my favorite questions to ask people is the Earth flat? And I think most people in this educated audience would say, even our grade 7, is the Earth flat? No, it's not flat. What is it? It's round. And most people would say, no, why are you even asking me this question? This is a stupid question. Is the Earth flat? The best answer I ever heard is the Earth flat. Somebody said, it used to be. And we love that answer because it sounds silly, but let's think about it. There was a time when everybody in this room would have said, yes, the Earth is flat. And we would have all nodded, and I would have said, how do you know? And they said, oh, we have experimental evidence. We look out at the horizon, it looks flat. Everywhere I've been, it looks flat. The Earth is flat. And the problem we have is right now, we say, oh, those stupid people thought the Earth was flat. We know the Earth is round. And in 500 years, they won't be looking at us as stupid people. They thought it was round. What are they, idiots? But they will be looking at us 500 years from now and saying, they thought it was round? Where did they get that idea? It used to be flat. Now we think it's round. No. We know it's round. We don't know anything. The editor of Nature magazine, one of the prestigious science journals of the world, they asked the editor of Nature, how many of the articles that you're publishing do you think will one day be proven false? And we all think of a number. His answer was, all of them. That's the nature of knowledge. We know. No, we don't. And that's what I was hoping to communicate with the electron. We think we know, but not as well as we would like to. And that's why we keep learning. That's why we keep going to school. Yes. I think you need a microphone. Oh, I'm sorry. You'll go next. Thank you.
Taking the larger topic of your talk, is it electron, a discovery, or an invention? And then the fact that it can be experimented with in controlled environment in laboratories tend to give it a physical construct or a connotation that it has a property to it. Is that more on the lines and it's more of a discovery rather than invention, like a mathematical function describing an electron?
I wish I knew. So if you ask a scientist about love, they will tell you, oh, there are pheromones. Well, if you're looking to attract somebody and you go out with them and you say, love is just pheromones, I don't think the relationship is going to progress very far. We can see aspects of love, but I don't think that's love. We see aspects of this and we get closer and closer to recognizing certain properties. And that's what we keep doing in science. We keep having new models to try to help us understand what's before us. Yeah, so I should caution this because most physicists don't worry about this. In fact, when you have a graduate student who's working for their PhD, if they start going down this path, well, do you think it's the many worlds interpretation or the Copenhagen interpretation of the electron? The professor does and should respond by saying, shut up and calculate. Do the calculations because we know the calculations work. Do the calculations so we can predict exactly what will happen. Don't worry about what's happening. Just calculate. So, we had a question here. Yes.
My question is, it's a wonderful science communication for the general public. Thank you for that. Thank you. Second question is, how do you explain for a science follower, not an explorer, about quantum entanglement?
So there are people who are working on this idea that if you take two electrons or two photons of light And you separate them, you put them here so you know they have similar kinds of properties, but you don't look at the properties. You just know they have different properties. And then you separate them, and you put one of them in Jaipur and one of them in Bangalore. And then, if you look at it one way in Bangalore, the person in Jaipur will see it that way. If you look at it a different way in Bangalore, the person in Jaipur will see it the different way. Instantly. I was like, wait, how did this piece of matter in Jaipur know the way you looked at it in Bangalore instantly? But it does. And so we think that because of this property, we can come up with ways to have secret codes so they can't get into my bank account, things like that, cryptography. So that's, I think you've now exhausted my entire knowledge of quantum entanglement. Yes?
I have two questions.
Okay.
One is, I think I know the answer that you're going to say, but I'm just going to ask it anyway. What is your take? Have we discovered or invented the electron? And my second question is, as a teacher, I'm sure you must have experienced that it's very frustrating when students are first introduced to quantum mechanics, as Bohr has said. Mm-hmm. On the one hand, there are all these things that we don't know about the electron, and on the other hand, there are all these wonderful technologies which are outcome of the electron. So is there some simple reading or reference, without going too much into calculations, which can help students bridge this gap?
So, in answer to your first question, because I've thought about this for some time, this invention or discovery, deep down, I think we discovered the electron. It really is there, it is real, but all of my intellectual thought says, no, we made it all up. But it's hard for me to believe we made it all up. In terms of students feeling comfortable with the quantum mechanics, maybe they shouldn't. You know, maybe they feel too comfortable with all the science we teach them, and that's why so many find it boring. And what you say frustrating as if it's a negative thing.
It doesn't help them understand, and yet they're given this magic wand saying, see, your cell phone is from that, this is from that, that is from that. But how on earth? They don't understand. I don't understand.
But you're leading a good life.
No, that's not the point.
I think that on the other hand, let's look at the other example. There are people I meet who say, oh yeah, I understand everything. My intuition is so good. I understand the world. I know more than the generals. Those people make me frustrated, make me angry. Because no, your intuition cannot be that good. I can give you too many examples where your intuition fails. And some of these people are running our world, have a great deal of power. And they're running on their intuition, and that frightens me. Because I would rather they have a scientific temper and use some evidence and some knowledge. So I don't know if frustration is a good or bad thing. When you know it all, I find that really distasteful. When I meet people who say, oh yeah, I know that. There's a movie that I like where this boy, he's in a secondary school, and there's a talent contest. I think it's called The Squid and the Whale. There's a talent contest, and the boy says, I wrote this song, and he plays a song. And nobody in the audience knows it, but everybody in the movie theater knows the song. It's a famous song by the Police, by Sting. And he wins the $100 prize. And then, of course, people find out you didn't write the song. Why did you stand there saying you wrote the song? And he said, as soon as I heard it, I knew I could have written it. And that's that idea that everything is so simple after somebody tells you. But there's enormous frustration. When I mean really, Beethoven, Da-da-da-da. How hard could that have been? All of the examples I gave you, it was the best of times, it was the worst of times. How hard? Come on. I can say that. Leonardo da Vinci, God touching Adam. Yeah, I could have thought of that. And so the people who don't respect the hard work, the creativity, that bothers me. Other questions?
Professor?
Yes.
There are two aspects, particularly.
I don't know where I'm looking.
Yeah, here.
Oh, okay.
Here.
Thank you.
To your left, above.
Thank you.
There are two aspects to the study of electron when it is concerned. First is when we say electron as a particle, it has some negative charge and it has some negotiable mass as well, which is definitely above the zero. But when we say electron as a wave, so how about this property conversion happens? Where are these aspects are considered when we say electron as a wave?
So the idea of localizing the electron, I don't know what it means. We know we can have the electron can be described as being multiples of many, many waves, because waves are infinite, to localize it to a certain area. We know the electrons stay near the atom, right. But what is waving? What is that? Is a wave, is it spread out? That's why it sees the two slits, but when it has to go through one, it collapses, we say. There's one of those theories about the electron being a wave or whatever, is a theory which says that it's not what the electron does, it's how we observe the electron. And when we observe the electron, we make a guess as to what the electron should do. And then when we get some data, we make a better guess and a better guess and a better guess, and there's no problem at all, it's just about our guessing. And without us to worry about the electron does just fine.
True. That can be considered as a hypothesis, though it has not come to the depth of granularity of the truth, right?
I'm sorry, please repeat.
So that can be considered as a hypothesis when we speak about the wave as an electron as a wave, right?
Yeah.
It has not reached the granularity of the truth, right?
So I went over that quickly, but the idea is that the uncertainty principle tells us that you can't know about where the electron is and what direction it's moving at the same time. It's delta P, delta X, but think of the momentum as a direction. So we send it through a slit, and we know it went somewhere through that slit. It may have been here, here, here. We don't know exactly where it went. And when we do that, we kind of have an idea of its direction because it lands somewhere in this area. If, however, let me just see if I can do this. My fingers are going to get tired. You're not going to be able to understand from my fingers if I have a slide. Let me see. Here we are. So the delta X is the position of the electron. We know the electron goes somewhere through the slit, but we don't know if it went through the top, the middle, or the bottom. And the direction it went in is those arrows on the right. It went a little bit to the left, a little bit to the right, but somewhere, the direction was somewhere. It didn't go it didn't go up. And so what happens is, the theory that Heisenberg came up with was, you can never know both those things. So if you want to know the direction, so if you make that slit smaller, so instead of going through the top, the middle, or having the choice, the top, the middle, or the bottom, it only goes through the middle or the bottom. If it only goes through the middle or the bottom, now we know more about its position. The direction spreads out. We know less about the direction. If we make the slit bigger, if we take away the wall, take away the slit, then we know nothing about how the electron got to the screen, but we know it goes in a straight line. You can't have both. And that was Heisenberg's uncertainty principle about the limitations of our knowledge. And the limitations are not because we don't have good enough instruments. The limitations are nature will not allow us to know any more than this, which is a peculiar idea. It's like, no, let's build an instrument so we can learn more. Nature won't allow it. It's just like covering up the slits. We're just stuck. Yes. Oh,
Professor? Question regarding the observer's bias and influence on some of these experiments. And could you throw some light as to what has happened in that area?
I was just reading about a book that came out 40 years ago about experimental bias. We would like to think that scientists are completely objective, but they're not. They're creatures of the culture they come from and things like that. So I don't know where the question comes from in that, certainly we don't, if a scientist is biased enough that they make up the results of their experiment, they will not get funded anymore. We have some strict rules about publishing false results because science depends on everybody working together. And if somebody produces false results, then everybody suffers because you believe this and it wasn't true. They made it up. So there's that kind of, not bias, but, just illegal, fraud. But as far as wanting to see certain results, it's hard not to see when you believe something so strongly. The expression that we have is that seeing is believing. But actually, the other expression is believing is seeing. You see what you believe. And so, way back with Galileo, when he dropped 2 balls from the Leaning Tower of Pisa, he writes in Two New Sciences, in his dialogue between the characters, that Aristotle predicted one ball would fall 10 times as fast as the other. One would take 1 second, the other would take 10 seconds to fall. When I dropped them, they hit the ground at the same time. But the other one says, oh no, they didn't hit the ground at the same time. I think one hit a little bit earlier than the other. And Galileo says, and so, he says, therefore I believe Aristotle. He says, wait, Aristotle was so far off. He said, I like Aristotle. And even though the intuition says the heavy balls should fall faster, when you do the experiment, they won't say the same thing, a little bit faster. In the 20th century, 1900, 1905, a scientist discovered N-rays. You've heard of X-rays, you haven't heard of N-rays. And a whole bunch of literature was about the properties of N-rays until somebody realized, no, they're not there. We just thought they were there. We believed they were there and we saw them and we were measuring properties. They didn't do this maliciously. They were just fooled by their strong beliefs. When you go home tonight, or you can do it now, but when I was working with some teachers today, if I take my cell phone and I turn it off, so now it's a mirror, I don't use the camera, use this. If I turn off my cell phone and I use it as a mirror, I only see this much of my head. I see from my head here to this part of my tie. I say, I'd like to see more, what should I do? And your intuition and common sense is, move the mirror further back. It doesn't work. It won't work. We think it should work. And in fact, when you do this, what people will say is, I think I can see a tiny bit more. Because they don't want to give it up. So believing is seeing, and I think that we try our hardest to be objective, but we're human beings. Yes? Oh, no, you've asked a question. Let's have a question here. Thank you.
With regards to the double slit experiment, could you, if possible, explain quite briefly the two most popular theories, Copenhagen and the information-based, and maybe some pitfalls of those theories?
Well, I tried to explain the, so one theory is called cubism, which I like so much. Quantum Bayonism. So Q-B-I-S-M. And that has to do with this idea of predicting what will happen. It has to do with the human being predicting it. The Copenhagen interpretation is the one that Niels Bohr came up with. I don't know how to say them simply, but there's a book that was written last year that somebody said, oh, you should read this book called Through Two Doors at Once. And the whole book, 150, 180 pages, is about the double slit experiment and all of the ways that people are trying to fool those electrons unsuccessfully through two doors at once. But the Copenhagen interpretation is the electron exists as both a particle and a wave all the time until you look at it. And by the nature of your experiment, it then becomes one or the other. So it has wave properties, and so we don't know where it is in the box. But as soon as we look, the wave function collapses to a point, and that's where we find it. And there's some kind of collapse of the wave function because we looked at it. And that's the Copenhagen interpretation. The many worlds interpretation is that the electron can go through slit A or slit B. If the electron goes through slit A, there's another electron. The electron also goes through slit B, but that is another universe. And in that other universe, the electron has gone through slit B, not in our universe. And everything that happens, every branching, creates another new universe. That's the many worlds interpretation. And these aren't even the craziest ones.
Excuse me? Sir.
Yes.
Do you have a personal conundrum in knowing that you will never know the reality in its true self and still pursuing the quantum physics and its research?
So I heard most of the question. I didn't hear the first. Do I have a
personal conundrum in this, and how do you deal with it if you have one?
I love it. I love it. I love the questions more than I like the answers. I love the idea I can't understand it. I remember when I went to school, I started university, and I was going to be a math major. I was going to major in mathematics. And I remember taking a physics course, and I couldn't understand it. There were just parts I didn't understand. The math I seemed to understand. And I decided, I want to study that thing I don't quite understand. It's just the way I like it. I like the mystery. So I like the world of conundrums in certain respects. In certain respects. I would like more certainty in other aspects. But as far as electrons, I'm okay. It's a fun game to play. And I think we have time for one more question, and then we should.
Good evening, sir.
We should stop.
Here.
Who has a microphone?
I'm here on top.
Yes.
Yes. So there were so many questions which religion couldn't answer. Science answered them. But what about the questions which science can't answer, like the one you explained recently, whether it's dual nature or an electron or wave nature? What do you think the people should follow for that?
Whether they should follow science or religion?
If the questions were not answered through science, where do you go?
The science and religion and the scientific temper again, they each have a place in our lives. And I don't want to pretend that the world is a better place if everybody just does science. So the example, we were talking about this just the other day, and I asked how many people got married on an auspicious day. They had somebody look up at their astrology table and said, this is a good day to get married. Now, I don't know if they believe that that's really a good day, but there's some respect for their elders, there's some respect for their culture, And they do it. And it makes them feel better to do that, and there's nothing wrong with that. On the other hand, if they don't vaccinate their children, and their children can get sick and die, now we have a problem with, it's not entertainment value anymore. So Niels Bohr, one of my favorites, so Niels Bohr, who was quite a philosopher in his own right, and we'll end with this. He had a horseshoe over his door. And he was asked, why do you have a horseshoe? And he said, I heard it brings good luck. And they said, you believe in that? And he said, no, but I heard it works whether you believe in it or not. Thank you very much.
The electron was just an excuse. Last time gravity was an excuse. That's how it will be year after year. Because I think the discussion, that's just a holder. Because the discussions that take place, his own lecture, plus the fabulous discussions that take place here, it's a much larger thing. There is a certain profundity, if I can say, a certain largeness. There's history, there's purpose, and much more. And I think we all go back, and I think this lecture and the questions and the answers will play in our mind much after we leave this room. For that, we need to thank you, Arthur, and we need to thank each one of you for being such a wonderful audience. Thank you very much. He pointed to my cricket and stuff like that, but I must tell you, Arthur, that I've seen young children come to your lectures regularly, but this time you've gone better. There's a couple of infants and toddlers also. Bye-bye, everybody, and thank you once again.